This is the Financial Thought Exchange podcast, where you get to learn from the leading thinkers in finance. I'm your host, Lotta Moberg, and I am now continuing my conversation with Oswaldo Zapata about quantum computing and especially how it applies to finance. Mr. Zapata is a co-founder of the Quantum Finance Boardroom, which is an online community advancing the use of quantum computing in finance. He is dedicated to bridging the theory and practice of quantum computing in finance, and he is the author of a chapter called Quantum Computing in Finance, which is part of the monograph AI in Asset Management. This is a collaboration between the CFA Institute Research Foundation and the CFA Institute Research and Policy Center. So thank you so much, Oswaldo, for your contribution.
No, thank you, Lotta.
And it's great to have you here for the next conversation here. And for those who missed the last episodes, make sure to check that out. You will learn everything about the basics of the technology here behind it. We go into very much the technical parts, and we'll get more into the application of quantum computing, and especially in finance now. And maybe I'll start off a little bit kind of where we ended up. We talked a lot about errors and why there are errors and what you can do about errors, that is, of the results of the computations that we perform in quantum computing. And I wonder what the implication of that is for finance today. So there are probably, I can imagine there are problems that we can solve with quantum computing that we can't now. What could you say about what kind of problems we're really not looking at right now because of these errors occurring too much, maybe compared to the more straightforward areas of application here?
Yeah. So the number of qubits we need in order to apply this number of qubits is just a measure, to give you an idea of where the technology is and the sort of problems we can solve. Okay, we said that 100 logical qubits, perfect qubits, would be enough to do some problems. However, we need, in fact, millions because these qubits are not perfect, right? And I say millions is not like a bit more than 100, is much, much more, right? So we need maybe 10,000 qubits just to correct one of these logical qubits. Okay. So here's the thing. I was reading them yesterday, and then I saw that I say quantum computers will not be available anytime soon. Something like this, I say. Okay. So I realized that this anytime soon is so relative. For example, if I say Mount Kilimanjaro will not erupt anytime soon, right? So this means not in 100 years, maybe not in 1,000 years, maybe not in 1,000,000 years, so maybe not in, in 100 million years. So when I say that in the, I meant in the near future, means 5-10 years. Okay, so in 10 years, it's expected that we will have the first real quantum computers where we can solve practical problems, right? Or maybe in 20 years, but not 100 years. Something that the technology is moving so fast that we expect to have what they call fault tolerant. And I will explain this, why fault tolerant quantum computers. So fault tolerant quantum computers are computers that have little errors, little number of errors, and the errors are corrected. Right? So the qubits are so good, the quantum gates are so good that even if errors occur, they will be corrected, and then you can rely on the computation of these machines. This is not the case now, right? So we are still in an early phase, research phase, where the number of qubits is small and it's very noisy, and that's why this year is called NISQ. NISQ means noisy intermediate scale quantum era. Noisy because, as I said, there's still a lot of errors occurring, and intermediate scale because the number of gates you can have in the circuit, in the quantum circuit, cannot be too many. If not, the errors will propagate, and then, of course, the results you will have will not be good. So then you need to do something before we reach this stage where you have fault-tolerant quantum computers. So they have these hybrid systems that I mentioned in the notes, where you have a bit of the computer is quantum and the other piece is classical. Okay, these hybrid computers, they will allow to solve some problems in the near future, or for example, portfolio optimization. These are algorithms that were developed for other areas of mathematics. Now they are applied also to portfolio optimization. One of the nice things about science and math is that you have the same description for so different problems, right? So once you have the same description, of course, you know that the solutions can be applied to any other problem that has the same mathematical formula behind, right? For example, this classical high school physics, you have the spring and the mass, right? So you have this mass oscillating, and then you write the equation. This equation is a simple harmonic oscillator. And then you say, okay, I will solve this problem. Fine. And then you solve the problem. And then you say, these are the solutions. But then if you see also the pendulum has the same mathematical description. So you know that the pendulum will oscillate when the angle is small, similarly as this pendulum. Okay, and then you have many other problems that have also this simple harmonic oscillator equation, even in quantum mechanics. Yeah? So this happens the same for example, for portfolio optimization. The equations that were discovered a long time ago by Markowitz and then some developments, the equations you have to optimize this system are the same that you find in other mathematical problems. Okay, so these experts around 10 years ago, maybe a bit more, maybe 12, they discovered that they could solve these mathematical problems by using these hybrid computers, classical and quantum. Okay, and then the mathematical problems have the same equations that describe portfolio optimization when you can whether include or exclude an asset from your portfolio, right? So they have been applying this, but honestly, the number of qubits is still too small in order to have some real applications, right? You have, for example, 10 assets, right? Because in this one of these algorithms that I mentioned, the QAOA, you have one asset corresponds to one qubit. But as I said, you need many, many more qubits in your system because you will have many errors, right? So it would be nice to have 100 perfect qubits, so you could optimize a portfolio of 100 assets. But in fact, the fact that you have all these errors means that today is still something not possible. So people expect that in, again, 3-5 years, we'll have more qubits, better qubits, not only more, but better qubits, so we can apply these machines to solving real problems.
So just to understand what you're saying, portfolio optimization, you mentioned Markowitz. This is a modern portfolio theorem, and where you have the possibility frontier between returns and risk. That is, while one of the most promising fields in finance to solve, still not something that is being done today.
Yeah, and quantum computers, they could help for that. However, as I said, the number of qubits, the hardware is not yet there. So we need to wait 3-5 more years. But of course, people are working in this area in order to be ready when the machines will be ready, right? So this is something is different than classical computers. When classical computers were discovered, invented, created, the software came much later, and people started thinking about how to program these computers after they were ready, the computers. Here's the opposite. We know that at some point we will have the computers, so we are trying to develop all the algorithm, all the software, everything in order to run these machines when they will be ready. Okay, so what we need still is the hardware. We need more qubits, we need better qubits, we need more gates. And this, of course, is not something, it's easier said than done, of course. So, but we are going backwards. Like, now we are developing. So many of the things you see today are still, let's say, on paper. Okay, just to make it clear, it's on paper, but not yet, running in real quantum computers. The applications of a real problems, solving real problems with quantum computers is called quantum advantage. Right? And then practical quantum advantage. This is something that hasn't been realized yet. Some problems, but only simple mathematical problems, have been solved faster with quantum computer quantum computers than classical computers. But these problems are not applicable to real problems, of practical applications that we are interested in. So we have proved that quantum computers are faster than classical computers, but only in four different problems. And these problems are not applicable to real problems, that we're interested in.
But you mentioned that there are such thing as this hybrid quantum and classical
Yes.
computers under development still, or is that a field where we actually do see? Is that going to be, if not today, then the first actual real life application then?
Yeah. So this is one of the hopes. Some people it's when you have this sort of emerging fields, not only practical like quantum computing, but also in theory, you have the community is always divided. Those that believe that this works, those that believe that this will go nowhere, right? So some people, honestly speaking, are very skeptical about these hybrid computers because you have a quantum computer that you have to plug to a classical computer, and maybe all the advantage that you can get from the quantum will be lost while you plug these two computers together. And the complexities are enormous. Okay? So it's not something simple, right? So this in machine learning, something similar happens. Sometimes you don't know how things work, but they work, right? These heuristics they call. So in quantum computing, it's the same. You have people hope that this will lead to some advantages. However, there is no mathematical proof that this will be so. So there are in fact um, some cases where mathematicians have solved, or computer scientists have proved that quantum computers will be faster, right? But portfolio optimization is not one of them.
Okay.
Okay. Yes, but as in quantum, in machine learning, in many things in artificial intelligence, sometimes you get results, but you don't know how the things are happening. It's simply the way it is, okay? Because the mathematics we use to solve these problems go beyond our capabilities. Okay? But however, machine learning works, and people say, okay, it's working for a reason, even if we don't know why it's happening like that. And this is not the first time, okay? When many things in science, in physics, for example, were discovered before people had a theory to explain why they worked. So this is the hope. The hope is that, okay, let's continue with this hybrid um, not machine, really algorithms, that then we will think how we will really realize them in the lab. But the algorithm tells you that there is a possibility of having some speed up there for
So
portfolio.
before we go to other hypothetical applications, if we just stay up on the portfolio optimization, that is an interesting one. So it hasn't been proven that quantum computing will help, and even the hybrid version. Still, you do emphasize that this is a hypothetically a promising application, right? And why is that so? Is it simply that it's computationally, just anything that's computationally complicated as portfolio optimization is?
Yeah, but so this problem is a very difficult problem. So it's a problem that classical computers will never be able to solve. And then, of course, they say, okay, let's try with quantum computers to solve these problems that we know that for classical computers, this will take ages in order to solve. Okay? The idea of this problem is just to find the minimum or the optimum of a function, right? For
Which is
example,
solved right now. I can do that in Excel, so that's not an unsolved problem, right?
yeah. So the idea of the quantum computer is to accelerate the process, or maybe find an approximation which is good enough, right? But you can find much faster. Okay? So in the case of portfolio optimization, as I said, is the mathematics is so complicated that you don't know, and the physics is even more complicated because you have the computer we have the classical computers we already have, but how do you plug these two brains which work completely different? It's at the intersection of these two. Maybe everything you can, all the speed up you can gain with a quantum computer can be lost when you plug it to the classical computers, because these hybrid computers, they work like this. You give to the hybrid computer, to the quantum computer, the difficult part of the problem, the part that that the classical computer will not be able to solve, right?
Yeah.
So you run the quantum computer, which is an adjustable quantum computer with some parameters. Okay, so you run here the quantum computer, you find a solution, you give it to the classical computer. The classical computer optimize, for example, a function, and then send it back to the quantum computer that shifts the parameter of the circuit, and then you do this in loop until you find a solution that you are happy with. Everything that I just described is easy to say, with this argument, hand waving argument, but it's very difficult to prove mathematically. It's nice when you have equations and you can solve equations. In theoretical physics is what I used to do, but when you really have to work with machines that are in the lab, this is completely different. And at that point, people say, yes, can be, but there is no proof that this will work. And then some people, they are skeptic that this is the path things will move. There are other approaches. There's, for example, one called quantum inspired algorithm. These are algorithms which are running classical computers, but they use the way quantum computers think in order to run these algorithms in classical computers. So instead of using the way a classical computer wants to work, or we know it works, they use the way quantum computers work to run the same, not the same, with the same purpose, another algorithm to solve the same problem, but using the way quantum computers use in a classical computers. Is that clear?
Okay, so if we go on that one, and I do want to talk about the iteration process. So please, listeners, remember that he said that, because that's an interesting one too. But on this point, right? It seems to be a little bit related, and that's another question too about like how we translate, right, a problem and information of a classical computer into a quantum computer, and this kind of resolves that in the sense that you don't have to have that translation communication going on.
Yeah, I understand what you're saying. It's the problems arise everywhere. Okay, when you when you want to even to encode classical data into qubits, that's the first step. You have, for example, numbers that you want to process in a quantum computer. Quantum computer doesn't know about numbers, right? Just knows about these states. So you need, for example, so let's say you have 10 numbers, which is nothing, okay? 10 numbers, and you want the quantum computer to process that. So you need to translate that into quantum states that the quantum computer will understand, right? So this, just at the beginning, when you want to insert your classical data in the computer, is already a problem. So imagine when you have millions of data, for example, or billions of data in machine learning processes. So the problems are huge, right? So for example, one thing they do that I mentioned also there, what they try to do is angle encoding. I told you that you can describe a qubit with two angles. In a unit sphere, you give only two angles. Every point in this unit sphere corresponds to a state of the qubit, of the single qubit.
And just to
Right?
point out, for the listeners who don't recognize that, that was in our prior conversation. So if you haven't listened to that already, I highly recommend it, because we're really getting into the technical nitty-gritty there. Go ahead.
Yeah. So you have you have a single qubit. A single qubit needs two angles to be uniquely described. Right? So you can have two classical data and be encoded in one qubit. Right? So if you have 50, okay, sorry, if you have 100 classical data, you can encode them in 50 qubits. Right? Here's the thing: when you have millions or even thousands of classical data, how can you encode them if we only have few qubits, right? The number of qubits we have is, as I said, is maybe 100, right? So we really need to go fast in order to encode all these classical data in order to be processed by a quantum computer. So even just at the beginning, when you have classical data and quantum computers, let alone when you have also the classical computer here, right? So just at the really beginning, you have this challenge. How can you translate this classical data so that the quantum computer will read it? And then after that, okay, when you make the measurement, you have classical data. Okay, you can send it to the classical computer, process that, and then send it back. But you have to shift, as I said, this classical data you will get from the classical computer will help parameterize this this circuit, because the circuit is depends on some parameters. Okay, you will shift the gates of the system, so you will send that back, and then you will run the process again, right, until you find a. This is very, very complicated. So that's what I'm saying. It's very early stages in the development these ideas, and so people have been thinking about all the possibilities, as the one I mentioned, of quantum inspired um, algorithms, where you run an algorithm in a classical computer, but the algorithm thinks as quantum computers would like to think.
Gotcha. And so if we go back to this iterative process that you're talking about, is
Mhm.
that a little bit similar to the people might be familiar with the Black Litterman when you're trying to optimize a portfolio and then you get a result, but you get the allocations and those allocations suggest what your risk and return will be. And then you can tweak that a little bit and then you keep going like that, like the return risk feed into allocations that in return feed and then until you get like a portfolio that looks like that doesn't have any corner solutions and looks reasonably kind of what you're looking for. Is that a fair analogy?
It's interesting what you're saying. I don't know. This is something we should look together maybe, but I don't know if there is nothing quantum there, in what you describe. So would not be
Yeah, you talk about
sense.
this iterative process. I'm thinking like, well, usually
Yeah,
iteration, right? If you have a recursion between two things, right, it's going to be
yeah, but
A, B,
no,
two
no,
different things. So what are the two different things is what I'm kind of trying to imagine and
but no,
analogy
no. Here,
old world.
here you need really here you need something that can be described by a quantum system, right? If you have a quantum system and then part of the iteration, yes, is quantum, yes, absolutely. So this could be applied to many, many other systems. In fact, one of the things that happen in quantum computing is that since it's still early, people are still thinking, there is no clear path where to find the ideas. So, for example, this QAOA was developed. I think I remember I was reading papers on quantum chemistry in order to understand how to apply this to portfolio optimization. So you see, so like the path, is very complex. You need to know where to go and then look. So what you are saying is possible because it's, for example, used in chemics, but quantum chemistry. Okay, so there must be this quantum part somewhere, right? And many of these, of course, these ideas come from purely quantum mechanical systems, as in chemistry, right? You have the molecules, the thing you want to find the optimum of this, the energy, the minimal energy of this molecule, and then you say, okay, these sort of systems are similar to mathematical problems that also are similar to these qubit problems that can be applied in a portfolio optimization. So it's a big mess, but this is what scientists are trying to discover today. Where to. Uh,
So I do think that the portfolio optimization is interesting. That's something that a lot of people recognize from their CFA textbooks, and we're used to doing this by hand, and we can do it in Excel, and we know we have better software out there, and maybe we're in the future at some point where quantum computers will solve this for us. Is there anything else to say there about kind of what we would expect or how this might actually work, and whether that will be, it's not feasible today, I assume, since a lot of this is in the future.
yeah, as I said, some people have been looking at other options to do this because it's can become uh, very difficult and maybe impossible to do it with these hybrid um, computers. However, the idea, as I said, before, is simply to use the quantum computer for the difficult part, and then it gives a set of results, classical results. You send it to the classical. The classical will tell the quantum computer, try now this, okay, and then the quantum computer will try another set of parameters, will speed another results, and then we say, what about this? And then the classical computer will do the process again and again and again. So this is the way you will find the minimum of the function. Okay, of course, in this case, the optimization of the portfolio. So um, now the research is very early stages. People hope that for the next, again, 5-10 years, when we will have maybe millions of qubits, we'll be able to optimize the first portfolios in practical and useful cases. right? Maybe with 10, 20 assets. Because in this algorithm, you need one qubit, one perfect qubit, this logical qubit, right, for each asset. But if you have 100 assets, you know that then you need also 10,000 extra qubits, physical qubits, in order to correct one of these logical qubits, right? So you need, in fact, around 1 million qubits in order to optimize a portfolio of 100 qubits, right? So it's not yet there, but soon. In fact, this is something I wanted to comment is when people say fault-tolerant quantum computers, like practical problems, we are talking about millions of qubits, right? Or 1 million qubits, 2 million qubits, 10 millions, and in this order. But we are still in the hundreds, maybe 150 something. And these are the company that claims to have thousands of qubits. These qubits, in fact, are not the same, are not of the same quality. By the way, this company, it is not the only company, but D-Wave is the name of the company. They develop another sort of quantum computer. These computers are not circuit based. The circuits that I mentioned in the previous discussion, where you have these qubits and you have the quantum gates, and then you have at the end the classical result. These are different systems. These are called quantum annealers, and then they can be applied specifically for optimization problems, like, for example, in this case, portfolio optimization. However, the quality of the qubits are not good. It seems that they have found some interesting results, but with 5,000 qubits, which are of very low quality. Okay? So I don't know if you get. No. So it's complex, not only the applications but also the hardware. If you try to do it with one of these um, base gate quantum computers, you will need 5 years, let's say, to have millions of these good quality qubits. In this case, in the case of D-Wave, you have low quality qubits, you have many qubits, and it seems that you can find some results, but still for portfolios of very small dimensions.
So it's early days, but I hope this conversation triggered some the imagination of our listeners about what could actually be possible with quantum computing in finance. Thank you so much, Oswaldo. This was our second out of 3 conversations on quantum computing in finance. A really interesting topic that there's a lot of attention to now, and we're really getting the nitty-gritty of where we are and where we might be going. And we will be talking more about where we might be going with this technology in finance, specifically in our third conversation. So make sure you do not miss that. Oswaldo Zapata, thank you so much. And thank you for contributing to the monograph AI in Asset Management, where your chapter is called Quantum Computing in Finance. And thank you so much for joining me for this conversation.
For more information, please visit rpc.cfainstitute.org/research-foundation.